Alright guys, so lesson 2. Today we're going to talk about domain and range and how you can tell what the domain and range of a function is by looking at a graph. From last class, you might recall domain is all the possible values of x and range is all the possible values of y. So you can kind of get a nice idea of what the answer is by looking at a graph. We should also know the difference between evaluating a function versus finding a solution. There's some similarities there, but there are some differences. So we want to make sure that we understand the differences between what those two things are. And we're going to learn how to evaluate or solve a function when I give you an equation, a table, or a graph. Okay, so those are 3 objectives. So let's refresh our minds here. So domain is all the possible input values, which is usually the x values. So when you're looking at a graph, x is the horizontal axis, right? So the question is, how far to the left does your graph go, and how far to the right does your graph go? Okay, if you just kind of put those numbers in there, then you'll have the domain. Range tells you what the possible output values are. What are the possible y values? In other words, how far up and down does your graph go? Okay, how far down, how far up? Okay, so that's what domain and range is, possible values of x and y. And the way we're going to tell it is by looking at a graph and looking how far left, right, up, and down it goes. Okay, so let's go ahead and take a look at this problem here. So first of all, I want to draw attention to the fact that there's no arrows on this blue curve. It has endpoints. So we have a solid endpoint here, and we have an open endpoint here. Okay, so let's go ahead and start with our domain. For the domain, we're going to start by putting an x here. We're going to put these little symbols, and then I'm going to put some blanks here and here. And what goes over here is how far to the left does this blue line go? Well, it stops right here on the left, right? Or I guess I should say it stops right there on the left, correct? So it stops at what x value? The x value it stops at is -3. So the farthest x value to the left is -3. Now, how far to the right does it go? What's the farthest x value to the right? The farthest x value to the right is 1. So this graph goes from -3 to +1. But we're gonna do something else here. Open dot means that it actually doesn't ever get to touch that point. So it gets infinitely close to it, but it never actually touches that point. So x cannot equal -3. However, we have a solid dot here. So the graph actually does reach x equals 1. So since it actually does reach x equals 1, we're going to put an equal sign here. I forgot to put the word right here. So what this means is that x can be anything from -3, but not including -3, all the way up to 1, including 1. Okay, let's go ahead and do the range. The range is pretty similar. It's just that instead of right and left, we're looking at up and down. Oh, did it backwards though. On the left side, we do down. So, looking at this graph, what's the lowest point on the graph? In other words, how far down does this graph go? Well, the lowest point is here or here. It doesn't matter which one you pick because they're the same. They both have the same y value. What's the y value? It's -4. Now, does the graph actually equal -4 though? Does it actually touch the y value -4? Well, let's take a look. Is there a hole here? Is there an open dot? No. Is there a hole here? Is there an open dot? No. So it seems to touch that point. So the answer is yes, the function can actually equal -4. So I'm going to put an equal sign here because the function actually does reach the y value -4. Now, what's the highest point of this function? Well, once again, there's 2 answers for that one, but they're the same. So the graph reaches its highest point right here and right here. Now, this is an interesting. So what y value is that? That's a y value of 0. Okay. Now, question: should I put an equal sign or not? This is a weird one because there's an open dot and a closed dot. But if I'm talking about the domain and range for the function, that means Does the function ever equal 0 anywhere? Yes, it does. It equals 0 here. Even though it doesn't equal 0 over here, because it never reaches that point, it does here. So we would still say that 0 is part of the domain, and so we would put an equal there, because it can equal 0 at some point. Now, if I had an open dot here as well as here, then that means the graph would never be reaching 0. Okay? All right. So that's domain and range. Let's do another example here. Now this time, notice that I've got arrows at the ends of this function. And what that means is it keeps going in that direction afterwards. Now you might notice these arrows, they're pointing in two directions actually. This one is going down and left. This one's going down and right. So the graph never stops spreading out to the left and right. It keeps going. So let's go ahead and we'll start with the domain. The question now is, how far to the left and how far to the right does this graph go? Well, since it goes down and left forever and it never really seems to stop going to the left, then it goes off into negative infinity. It never stops. Same thing for the other side. It goes down and to the right forever as well. So that's positive infinity. And so what that means is that x can be anything. Any number you want to, from negative infinity up to positive infinity. So another way to write this is all real numbers is what the domain is. So this one's kind of like a linear function. Linear functions are like this. You can plug in anything you want to for x and you'll always get an answer. Same thing for this. Since the graph goes to the left and right forever, and there's no holes or gaps or jumps in this function anywhere, you can definitely just say it's all real numbers. Now let's take a look at the range. Range is the y values, and we're looking at the lowest and the highest point. Let's start with the highest point. That's pretty easy. What's the highest point of this graph for y? It's 10. And does it actually reach 10? Yes. There's no open dots there, so it actually touches 10. Now, how far down does the graph go? It never stops. It's infinite. So you can write your answer like this. But another way you can write it is you could just write this. That really means the same thing. Because there's no sense in saying y is less than 10 and greater than infinity, because that just means that it never stops going down, and so does this. It just y can be anything less than 10, so it never stops going down. So you could write it like either way. That's fine. It doesn't really matter. By the way, there is another way to write the domain and range, and I would encourage you guys to write this as well. So let's talk about notation a little bit here. This is something you're going to want to write down on your notes for sure. Okay. First of all, you guys will notice that I didn't put equals here, right? And I didn't put it here either. You can never reach infinity. Okay, so don't put equals if it's going to infinity. Because if infinity means it never stops. That doesn't mean anything to say you can reach infinity because it never stops. So we're never going to put equals there. All right. But I want to show you guys another way to write these notations here. So let me clean it up a little bit. So my first one looked like this. My second one looked like this. I want to show you guys another way mathematicians will often write the domain and range. Okay. Anytime there are inequality arrows without equal signs, we use parentheses for those ones, and then you put the smallest number on the left and the biggest number on the right. It looks like a point. It's not. It's an interval is what we call it. Okay, now for this one, we put a parenthesis on the left, but on the right, see how there's an equal sign? Since there's an equal sign, for that one we would use a bracket. Smallest number on the left, biggest number on the right. So these are different ways to write an interval or a range. You can write intervals with inequalities, or you can use these parenthesis and bracket notations. Okay, let's go ahead and take a look at another one here. Which one do I want you to use? You may be wondering. Just know how to do both. I don't care which one you use necessarily, but I do remember that I think there might be a couple on the homework where they write it in the bracket parenthesis way. So it's a good way you want to know both. Okay, let's go ahead and take a look at this one here. So let's do the domain. Domain is all the possible values of x. And on the left, we're going to put how far to the left does this graph go? Well, on the left, there's an arrow. That means it never stops going to the left. So we're going to put negative infinity. Notice it's negative because we're going to the left. How far to the right does this go? It seems to stop right here at this closed dot. So the farthest point to the right is 5. And since it's a closed dot, we're going to put equals. Now another way that you could have written this would be open parenthesis, because it doesn't equal negative infinity, comma, 5 with a bracket, because it does equal 5. All right, let's do the range. Range is up and down. So what is the lowest point on this graph? Well, it never stops going down, so that's negative infinity. What's the highest point? It's 2, and it can equal 2. If you want to use the bracket or parenthesis notation, it would look like this. Parenthesis for the infinity, bracket for the 2. It can't equal negative infinity, but it can equal 2. So all the possible values of x are from 5 and down, and all the possible values of y are from 2 and down. Okay? Here's one more. Now, I brought this example up because it's a special kind of function. It's an exponential function. But what's kind of interesting about it is it has a horizontal asymptote. That's something you probably should have heard about last year in Algebra 2. And I'll refresh your memory. What is a horizontal asymptote? It's an imaginary line that your graph gets closer and closer to, but it never actually reaches it. It never actually reaches it. Okay? And that's why the line looks really, really flat the farther we go to the right. But it never really actually is flat. It's just getting more and more flat as we get farther and farther to the right. It's a weird thing. It blows your mind, but that's how it is. So, domain, possible values of x. Oops, I put an equals. Maybe not want that. We'll see. Now, how far to the left does it go? Well, we have an arrow, and the graph is going to the left, so it must be going to the left forever, so we'll say negative infinity. How far to the right does it go? Well, there's an arrow, and it's pointing to the right, so there's no reason to assume it's ever going to stop going to the right. So we would say that the domain is from negative infinity to positive infinity, also known as all real numbers. So there's no, you could plug in anything you want to for x, in other words. Okay, let's do the range. How high up does this graph go? Well, it seems to go up forever. This arrow here tells me it gets higher and higher and higher. So the highest value is infinity. It never stops going up. How far down does it go? You might be tempted to say negative infinity because I told you it gets closer and closer to this line, so it keeps getting lower and lower, but it never crosses that line. Okay? So it's limited by that line. It's like an invisible barrier it can't cross. So it cannot cross what y value, and it can't reach what y value. It cannot reach 0. Okay, it's getting closer and closer to y equals 0, but it will never actually touch the x-axis where y equals 0. And since it can't touch it, we're not going to put an equal sign underneath it there. So for asymptotes, we don't put equal signs either. And so this would look like this. Okay? And all that's just a fancy way of saying y can only be positive. It goes from 0, not including 0, up to infinity. That means that y can only ever be positive. Okay? So that's domain and range. Here's a couple for you guys. If you want to pause the video, when you unpause it, you will see the solutions. Okay, so there's the answers for numbers 1 and 2. Now, number 3, I didn't put the answer yet because that one's a little bit complicated. I realized maybe it was a little bit unfair for me to give that to you at the moment. But let's go ahead and talk about it. basically what we're looking at here is we're looking at a type of function which has two pieces to it. Okay? There's one piece and there's another, but they'll never be able to be connected because they have those dotted lines in between them, which are asymptotes. It has the orange vertical asymptote you see there, and it has the pink horizontal asymptote. So these two pieces of the function are broken off from each other, and they'll never be able to be connected. And believe it or not, even though that graph has two different pieces to it, that actually is one function, even though it has two pieces. You don't know this yet, but this is that's the picture of the function that you're seeing right there. So it's interesting. Some functions, when you graph them, are broken up into two pieces. But anyway, let's go ahead and talk about the domain and range a little bit. So here's one way you can talk about the domain and range. You could just do the domain of one piece and the range of one piece, and then do it for the other one. So like, for instance, for this one over here, we have, let's go ahead and work with this left piece over here, this one. Well, there's no arrows, so I intended there to be arrows, but if you treated it like there wasn't arrows, then I'll show you what you would have got. But let's go ahead and say there were arrows first, and then I'll show you what you would get if you didn't think about them going on forever. So, well, the graph never stops going to the left, but it does have a barrier on the right. That orange dotted line is like an invisible barrier it can't cross, so it can't reach 2. So that's one way. Now, if you didn't think that like I wanted it to be, but that's my fault. If you didn't think of it as an arrow, then maybe 1, 2, 3, 4. Maybe you put -5 here, and that would be fine because I didn't put arrows. So maybe you thought it actually just stopped here at -5. That's fine. But notice how now if you did put -5, I didn't give you an open dot there, so it's kind of. Once again, should you have put an equal sign here or not? Well, it just depends. It was my bad. I should have been more clear on that. But anyway, let's go ahead and show. So the other way to write that, of course, is with parentheses, or maybe you could have put a bracket here on the 5 if you thought of that as a closed dot. Okay. So there's that. Now we also can do the range. All right, so the lowest point, if you want to think of it as infinity, is it never stops going down. But it does have an upper limit. The graph, this blue line, cannot seem to cross that purple dotted line, and that's where y equals 0. So there's one answer. Now, once again, maybe if you didn't think of the endpoints as arrows, but maybe as a solid dot, once again, it looks like it would stop at -5 to you, so maybe put -5. And same thing applies if you wanted to do the notation over here. Maybe you used a bracket, maybe you used parentheses. It doesn't matter. But if you chose to put infinity, then you have to use parentheses, remember, because you can't really reach infinity. So whatever way you want to do it. That's one way to do it. And then, of course, repeat that process over here. I'm not going to give as much explanation on this one, but so basically, you could just find the domain and range for each piece, but once all this is said and done, I'm going to show you guys something kind of interesting here. All right, so there's my answer for this other piece up here. Now, what I want you guys to notice, though, is that if this graph really does go from -infinity up to 2, and then from 2 up to +infinity, well, basically, we're going from -infinity to 2, right, on the left side, and then from there, we're going from 2 up to +infinity. Well, but guys, that basically means everything's included. The only thing that's not there is the 2 because we have that dotted line there. So here's another way that you could say the domain for this particular problem. You could say all real numbers except 2. That would be fine. So the domain, what are the possible values of x? Well, it's everything except this dotted line. In the same way, for the range, the graph goes from -infinity up to that purple line, and then it goes from positive infinity down to that purple line. So the only place the graph can't seem to touch is this purple line. So for the range, you could say all real numbers except y equals 0. So just remember, I mean, this is a nice little formula. I don't plan on giving you guys something this tricky like on a test or a quiz, so don't worry. But just want to get you guys thinking about what domain and range is. It's just all the possible values of x, all the possible values of y. And this is generally how you're going to write your answer, but sometimes you can get creative. So I think that the point's been made. Just make sure you know what domain and range is. If you got numbers 1 and 2, then you're pretty much on point. The only thing I'm concerned about on number 1 is maybe you weren't sure if you should count this as a solid dot or not. I would say as a general rule of thumb, if they don't actually go out of their way to put a open dot there, if they don't actually go out of their way to do that, then you can assume that that's a closed dot, okay? But if you assumed it was an open dot, it's fine. You got the point. It doesn't really matter. I'll try to be less vague on tests and things like that, so you won't be so confused. But anyway, let's go ahead and continue here. Let's talk about our second objective for today. So we talked about domain and range. Now I want to talk about what does it mean to evaluate a function, and what does it mean to find the solution to a function. They actually have something in common. Okay, but they also have some differences. So let's see what it is. Evaluating a function. Evaluating a function is when I give you an input and you find the output. So for instance, here's a function. If I give you an input, like let's say 3, and your job is to find the output, that's what we call evaluating a function. All right? Now finding the solution is similar because you're going to plug something in and get an answer, but it's the opposite actually. Finding a solution means I give you the output and your job is to find the input. So for instance, that. So, and by the way, every input should only have one output. So with this input, I should only get one answer. So when you're evaluating a function, you should only get one answer because inputs only have one output, which is what we learned in our last lesson. But when you're working backwards, that's not necessarily true. Outputs don't necessarily, well, I guess I should say it differently. Outputs are not necessarily associated with one input. So you can get, it's possible to get more than one answer. Okay? So that's what evaluating a function and finding a solution means. And you guys can see that what they have in common is the idea of you're plugging one thing in and getting the other. But the difference between them is evaluating is when you plug in the input to get an output. Finding a solution is when you plug in an output to get an input. Finding a solution is kind of like working backwards, if you will. But that's actually what most of algebra is. You know, remember back in Algebra 1, they give you all kinds of equations, and they say, find the solution. Right? All right, let's go ahead and look at example 2 here. Find each indicated value and determine if we are solving or evaluating. So I'm giving you a function here, f of x equals 2x minus 3, and then I've done this. So I'm giving you the input, and I'm asking you to find the output. Now when we do that, that is an example of evaluating. So let's go ahead and evaluate. So I'm going to take my function, and evaluating means I'm going to replace the x with the number they want me to, which in this case is 3. So I'm going to plug in 3 for x. Following our order of operations, 2 times 3 is 6, take away 3 is 3. So that's evaluating because I plugged in for the input and I got the output. Now the next one here, f of x equals 8. In this case, I don't know what the input is, but I do know what the output is. So for this problem, I'm giving you the output, but asking for the input, and that is whenever we are trying to solve. Okay? So how do we do that? Well, in this case, we take our function 2x minus 3, and we put 8 where the output would be. So since, here's another way you can think about it. Since f of x equals 8, I can replace f of x with 8. Okay? From here, we're going to solve for x. Using old school algebra. So that's what evaluating is, that's what solving is, and this is how you do it in each case. So let you guys try one like this. Same thing, you want to tell me, is this evaluating or is it solving? And then I want you to go ahead and find the missing variable. Okay, so pause the video. When you're all done, I'll have the answer up. All right, so there you guys go. Now some of you guys might be wondering, Mr. Bailey said sometimes when you're doing solving, you can get 2 answers. Well, we haven't really gotten there yet, so you have to worry about too much. But here's an example. Suppose I gave you guys this. I guess this is fine. So let's just say you set up a problem like this to solve it, right? Well, whenever you solve this, you take the square root on both sides and you get 2, right? But guess what? You also get negative 2. There are 2 numbers where if you square them, it's positive 4. So that's an example of when you're solving, you can get 2 answers. But in this case, it's not happening. And since we haven't talked about these types of functions yet, quadratics, I'm not going to be testing you guys on those. So for now, even though you can technically get 2 answers with solving, you probably won't be because I'm not going to be giving you anything else other than linear for now. All right, let's go ahead and move on to example 3. We're going to do the same thing. We're going to do evaluating and solving, but this time we're not going to do it with equations. We're going to do it with tables and graphs, okay? Now, I have 2 functions up here, and they are different. So this one here is the f of x function. You can see that I've named it there. And then this one here is the g of x function, and I've named it here. So I've given to you f of x in the form of a table, and I've given to you g of x in the form of a graph. Okay, so we're going to learn how to evaluate and solve functions whenever we're looking at graphs and tables now. Okay, so without any further ado, let's get down to business here. So for number 1, it's talking about f, the function f. So I'm looking at the table right now. I'm not looking at the graph, and it's asking me to find out what is f of 0. Now you can tell here, first of all, notice that there's no repeats here and there's no repeats here. So you might be wondering, well, now, Mr. Baird, there's no repeats. How do I know which one's the input? Well, because I've given you this notation here, you know that x is the input. Okay? So in this case, not f of x, but since the x is in parentheses, I know that x is the input and f of x is the output. A little something we talked about yesterday. So in this case, f of 0, what we're doing is we're plugging a number in for x and we're getting out an answer for f of x, which is y in this case. And that would be looking for where x equals 0 and then find the f of x that goes with that, and it's 9. And that's an example of evaluating. I'm going to put an E there for evaluate because I gave you the input and I asked for the output. All right. Let's go ahead and jump down to this number here. I don't know why I've got 2 3s, but let's go ahead and jump down here to the second number 3. In this case, this is an example of solving. So I'll put an S there for solving because for this one I'm giving you the output and I'm asking for the input. Okay, so since f of x equals 3, for this one, I'm going to look for where, f of x equals negative 3. I'm going to look for where f of x equals negative 3, and then I'm going to look for the input that goes with that, and the answer is 2. So x equals 2. Okay, so when you see this, you start in the x row, but when you see something that looks like this, you start in the f of x row. Okay, and that's the difference between solving and evaluating. Now that's with the table. Let's go ahead and jump on over to the, matter of fact, before we move on, why don't we stop there for now? And I want you to go ahead and do your student practice here. want you guys to do the same thing. I want you guys to evaluate and solve these two problems. So go ahead and pause the video, and when you're done, you will see the solution up. Okay, there you go. So the first one there was evaluating, the second one was solving. All right, let's go ahead and backtrack a little bit. Now we're going to go back to the teacher example. And now we're going to, all the other questions, number 2, and then the one after it, the first number 3, and then the last 2, those are all about the g function, which is over here on the right. So for this one, we're going to be looking at the graph. Okay, so in this case, when the number is inside the parentheses, that's the input. And as you guys remember, input is the horizontal axis. So in this case, basically what that means is that's an x number. It goes on the x-axis, so -4. So I want to find, where does my graph, where does this red line have an x value of -4? And that would be right here. Okay? That's where my graph has an x value of -4. Now, what are the coordinates at that point? Well, of course, the x value is -4, but what's the y value? It's 0. Okay? So, g of -4 is saying, okay, this is x, so what's the output? And in this case, the output is the vertical axis, which is y. So in other words, if this is x, what's the y that goes with it? Well, just take a look at your point. What's the y that goes with the -4? It's 0. Okay? Go ahead and do another one here. Now, for number 4, g of x equals 1. Now, in this case, I'm not giving you the x. I'm giving you the output instead. And when you're looking at a graph, the output is the vertical axis, which usually is going to be the y variable. Okay? So I'm telling you y equals 1. So here's where y equals 1, right? But that's not on our graph. Remember, the graph is this red line here. So where does my graph have a y value of 1? Well, that would be right here. Don't you guys agree? So at that point, I have a y value of 1. Now, what's the x value that goes with that y value of 1? What's the x value at that point? It's -2. And that would be the answer to this question. So basically, what you guys need to do is you need to decide, is the number that they're giving you an x, or is it a y? Find the point on the graph that has that x or y value on it, and then give the other number that goes with it. Okay? Let's do one more. Let's take a look at number 5. So on number 5, is this an x or a y? Well, since it's an output, that's a y value. So I need to find where at on my graph does y equal -4. Well, y would be equal -4 right here, right? But we have a problem. Even though y equals -4, what's the x value at that point? It's 2. But here's the problem. You may notice that's an open dot, which means even though that's the point, right, the problem is open dot means that point is not actually on the graph. And so this one actually has no solution. Now, if I had this bubbled in, if that was a solid dot, then the answer would be 2. Okay? The x value that goes with that y value would be 2. But in this case, since it's not bubbled in, it's an open dot, that point actually doesn't exist on our graph, and therefore we would say for that one that there's no solution. Okay? So, now that we know how to evaluate and solve with graphs, I want you guys to do the same thing on this student practice here. I want you guys to do numbers 2, 3, 4, and 5. Go ahead and do those 4 problems, and we'll see how you guys do there. Okay? Pause the video. When you unpause it, you will see the solutions. Okay, so I've color-coded these, so that way you guys can take the answer that you see on the left and match it to the point on the right. So for number 2 there, the point is 4, -3. Wrong color. There we go. There we go. So it's 4, -3. So when x equals 4, y equals -3. All right, for the next one, g of 1, the 1 is an x value, so we look for where x equals 1. And this is the point that we would use. Now, there's actually 2 points where x equals 1, but the answer is -3. We're not going to use this one. Even though for the orange point there, the x value is still 1, the problem is it's an open dot, so that doesn't work. But right below it, we have a solid dot where x equals 1 as well. And the y value that goes with that is -3. Let's go ahead and take a look at the next one there. Oh, did I do that wrong? I think I might have put the answer in the wrong place. Let me move that. There we go. Technology is sometimes a good thing. Okay, so for number 4 there, g of x equals -2. Well, in that case, we're saying that the y value is -2. There's only one point on our red line up here where there's a y value of -2, and it's right here. But the problem is it's an open dot, so it doesn't exist. If it was a solid dot, we would say the answer is 1. But since it's an open dot, there's no solution. All right, let's go ahead and take a look at number 5. For number 5, there says g of x equals 6, and that's the blue dot at the very top you guys see there. 6 is a y value, and that's where on our red line we have a y value of 6. So the x value that goes with that is -3. So that's evaluating and solving with graphs, and the first 2 were examples of evaluation. The last 2 were examples of solving. Okay? All right, so that takes care of our lesson for the day. So we'll see you next time.